All right, we're going to do the last chapter of the course now, which is chapter 7. And we're back to solving triangles, but unlike the triangles we solved in chapter 2, these will not necessarily be right triangles. So now we're going to be able to solve every triangle we come across. Okay, so let me just remind you what solving a triangle means. Solving a triangle means determining the measures of all three sides and all three angles. All right, so let's take a look at a generic triangle that's not necessarily a right triangle. Now, if you recall, our naming convention is that we used capital letters to represent the angles, and we used lowercase letters to represent the sides, and specifically, the side lengths were named using the same letter as the opposite angle, but lowercase version. So this will be side B, and over here will be side C. And this convention is especially important for the law of sines because the formulas we're going to see will very specifically be referring to A's and B's and C's in their relative positions. Okay. Now, of course, what we want is a formula to relate all these sides and angles here, but we do not have a right angle, so we can't just directly appeal to SOHCAHTOA trigonometry as we've been using it. The way to fix that is by drawing a vertical line here, which is called an altitude. And we're going to call that H for height. And we have a right angle down here, and we actually have another right angle down here. Okay. Now we have two smaller triangles that we've broken the main triangle into. And in each of those smaller triangles, we have a right angle, so we can use SOHCAHTOA to make these relations. Okay. So for instance, in this first triangle, we can see that sine of the angle capital A is little h over little c, okay, opposite over hypotenuse. And if we solve for h, we can see that little h is little c times sine of capital A. Okay, very good. Now, on the second triangle, we can see that sine of capital C is little h over little a. And therefore, solving for little h, we get that little h is equal to a times sine of capital C. All right, well, both of these h's are equal to each other, which means we can equate their right-hand sides. So we can conclude that little c times sine of capital A is equal to little a times sine of capital C. All right, and in fact, by dividing both sides by AC, we can see that sine of capital A divided by little a is equal to sine of capital C divided by little c. And that is the law of sines. Notice that we now have a formula relating A and C that doesn't depend on H. So in fact, if we just rearrange all the labelings, we can see that we can equate sine B of B over this as well. So let's write down the law of sines. So in any triangle ABC, we have the following fact. Sine of capital A over little a is sine of capital B over little b, which is sine of capital C over little c. And in fact, it's often convenient to use the reciprocals here to write this as a over sine of capital A is equal to b over sine of capital B is equal to little c over sine of capital C. Usually we'll use this version of the law of sines with the unknown angle on top if we're seeking the unknown angle, or use the bottom one if you're seeking an unknown side, little a, little b, or little c. Okay, so before we go on and look at any examples, there's also a law of sines for area. So note that the area of this triangle would be 1/2 times the base times the height. However, recall that we learned that h is equal to c times sine of capital A. And therefore, the area is 1/2 b times h, which is c times sine of capital A. And that's one version of the law of sines for area. There are actually 3 ways to write this because you can permute the letters A, B, C any which way. So we can also write this as 1/2 AC times the sine of capital B, or 1/2 AB times the sine of capital C. All right? So in other words, you can think of the law of sines for area as just multiply any 2 side lengths together and multiply by the sine of the angle between those 2 sides. Okay, so for example, this first one here is 1/2 B times C times sine of the angle between B and C, which is A. All right, this is the law of sines for area. So using the law of sines, we're now equipped to solve triangles, getting the lengths and angles of triangles that are not necessarily right triangles, and we can also find the area easily of any triangle. So let's go look at some examples. All right, well, here we have a triangle to solve for, and we're given a little bit of information, 2 of the angles and 1 of the side lengths. So we should make an attempt to draw this triangle. Now, I want to point out that it doesn't really matter how you draw it. You can just ignore the actual measurements given and draw your triangle and just label the sides, A, B, and C, and then just see what you're missing and use the law of sines to work out what you need. However, I will make some attempt to draw this triangle correctly, just to show you that the law of sines is enough to properly determine everything we need to know about this triangle. So what are we given here? Capital A is 28.8 degrees. So, okay, well, I won't be able to draw exactly 28.8 degrees, but I usually put angle A down at the bottom here, and that's about a 30-degree angle. So maybe call that angle A right there, and that's part of our triangle. We also know that side C is 25.3 inches, and side C I usually draw right up here. So let's just decree that that is 25.3 inches exactly. All right, now the angle opposite side C is of course angle C, and we need to put that somewhere. That angle must be 102 degrees. So we just need to put that in a location so that it's 102.6 degrees. And you can see that that would be right about here. Okay, and now we'll just label the rest of our triangle and see what we're missing. Now, the easiest thing to find here is that missing angle capital B. So let's go for that right now. So I get 48.6 degrees for capital B. All right, now we're going to use the law of sines to find little a. Okay, now in order to use the law of sines to find a missing side or a missing angle, you need to at least have the opposite of that known. So we can use the law of sines to find little a because we know what capital A is. But you also need to have a known angle and opposite side pair elsewhere in the triangle. And we're good because we have the CC pair here. All right, so we're good to use the law of sines to find little a. And we're going to use this version of it with the unknown side in the numerator as opposed to the reciprocal. So we're going to say little a over sine of a is equal to little c over sine of big C, because those are the given, and we're interested in little a. So solving for little a, we can see that this is little c times sine of big A divided by sine of big C. So that's 25.3 inches times sine of A, which is sine of 28.8 degrees, all divided by sine of 102.6 degrees. So doing the calculation, I get 12.4891. And rounding according to the precision in the problem, we'll write that as 12.5. Okay, however, if we're going to need A for any further calculations, we need to use as many digits as our calculator is showing. All right, now let's find B. Well, of course, we're going to use the law of sines as well, so we'll have B over sine of big B is equal to C over sine of big C, because we were given the C-C pair. Now, we do know the AA pair at this point, but it's really good principle, of course, to appeal to the givens when all things are equal, so that in case you made a mistake calculating A, you're not propagating that error through the rest of the problem. You're keeping it sequestered. So let's solve for little b here. So that's little c times sine of big B divided by sine of big C. And we have that information given. So little c, 25.3 inches. Big B was 48.6 degrees. Sine of and big C was given as 102.6 degrees. All right, so we'll just do that calculation. So I get 19.4461, which will round to 19.4 in our answer there. So this is the triangle solved. We now know all three side lengths and all three angle measures. All right, in this example, we are only given one angle in the triangle, so we can't just use the 180 degrees trick to find the other angles. You need 2 out of 3 angles to do that. So we're going to have to appeal to the law of sines. And in order to use the law of sines to figure out anything, you need to have already known an angle and opposite side pair, which fortunately we do here. The 41 degrees and the 35 meters are known and they're opposite each other. So we're good to go on that. Okay, which means that since we're given the 32 meters down here, we're able to use the law of sines to find the angle opposite that 32 meters. And from that point, we will have 2 angles, which means we'll be able to use the 180 degrees trick to find the last angle, and then finally the law of sines one more time to get that third side. So, all right, we have our work cut out for us. So let's label the vertices of this triangle so we can refer to things. And I'm just going to use the capital letters here for the vertices. And I will omit the explicit labeling of the lowercase sides because we know how they're going to be labeled based on our capital letter arrangement. So that means we're going to look for capital B first. All right, and because we're looking for an unknown angle, we're going to use the law of sines arranged in such a way that the unknown angle is in the numerator. So I'm going to sine of capital B over little b. Okay, and we're going to use the AA pair, which we are given. And therefore, sine of capital B is little b times sine of capital A divided by little a. Okay, so sine of capital B is little b, which is 32 meters, times sine of 41 degrees, all divided by little a, which is 35 meters. And notice that the meters cancel. They're actually providing us with a unitless ratio here as the sine value would be. So let's do that calculation first. And then we will take the inverse sine of our answer to obtain capital B. So I get this ratio as 0.599825. And so therefore, B is the inverse sine of that ratio. So make sure that you're in degree mode for this, and I get capital B is equal to 36.8574. Okay, so very good. We know what capital B is. And we'll round it to the precision of the other angles in the problem for our final answer. Now we can find capital C. So of course we know capital C is 180 degrees minus capital A minus capital B. And because we're using B in a calculation, we should use the calculated version of it. So I get 102.143, which we'll write in our final answer up here as 102 degrees. Okay, so finally we just need to find little c, and for that we'll use the law of sines. But since we seek an unknown side, we'll use c over sine of c rather than sine c over c. And we could use the BB pair because we now know angle B, but as usual, like always, we should appeal to the givens if we can. So we'll use the AA pair. So this is A over sine of capital A. So little c is A times sine of big C over sine of big A. So little a is 35 meters times sine of big C, which is 102.143 degrees, all divided by sine of big A, which is 41 degrees. So I get little c as 52.1553 meters, which we will write in our final answer as 52 meters. So we have solved this triangle. We are also asked to find its area. So again, we can use any two sides and then the angle between those sides. So I say since we were given A and given B, let's use A and B, and we'll use angle C. Right? So we're minimizing the number of values that we had calculated in our calculation at this point. All right, so little a was 35. Little b was 32. And capital C we calculated to be 102.143 degrees. So I get an area of 547.471 square meters. Now notice that the original given information had two significant figures, so we do need to round this to two significant figures. So that would be 550. So we'll say the area of the triangle is 550 square meters. Okay, so here we have a situation where we want to know the height of a building, and we know a few things, like the height of the flagpole is 95 feet. So let's write that in. But we do not know the height of this building here. So let's call it H. We also know that the angle of elevation to the top of the pole from the point on the ground that we're interested in is 35 degrees. So let me just say that's a 35 degree angle. And the angle of elevation to the bottom of the pole from the ground is 26 degrees. So that's a 26-degree angle there. Okay, and we can probably presume this is a right angle building here, built straight up and down. So question is, how tall is the building, right? So let's find h. Okay, well, we solved problems like this in chapter 2.5, except they were really annoying to solve. You'd have to set up a system of equations using h plus 95 and a bunch of different tangents and so on. And we were able to get through those, but with the law of sines, this problem becomes a lot easier. And that's because we actually have a triangle here that's not a right triangle. And we know an angle on it, and we know a side. So the angle here is 35 minus 26 degrees, right? So that would be 9 degrees. So in that triangle, we have an opposite side and an angle known, which means we should be able to use the law of sines to get any bit of information we want out of that triangle. But we're going to need another angle. So, well, let's see. Can we figure out this angle up here? Well, yes, we can. Okay, because we can figure out this angle. So this angle right here is the complement of 26 degrees because of the fact that it's the other acute angle in a right triangle. So 90 minus 26 is 64 degrees. Okay, and that means that this angle right here, which is the supplement of 64 degrees, is 180 minus 64, which is 116 degrees. All right. And if we know that that's 116 degrees, then we can figure out this angle right up here. Okay, because that angle right there is going to be 180 degrees minus 116 degrees minus 9 degrees. So that's 55 degrees. Okay, so yeah, we've learned a whole bunch of angles, big deal, but why is that helpful? That's helpful because we can now use the law of sines to find that particular length. Okay, and we know if we call that length, say, x, then we know from the law of sines, we know that x divided by the sine of its opposite angle, which is 55 degrees, is equal to 95 feet divided by the sine of its opposite angle, which is 9 degrees. Okay, so we can solve for x by moving sine of 55 degrees over. So x is 95 feet times sine of 55 degrees over sine of 9 degrees. So I get that x is equal to 497.457 feet. Okay. Now, how's that going to help us? Well, remember, we're after h. Okay. And we know what x is, and of course we know this angle down here is 26 degrees. So that means that we can simply use SOHCAHTOA to find h, because that is a right triangle. Indeed, the sine of 26 degrees is equal to h over x, opposite over hypotenuse. Okay, and here h is the opposite. So solving for h, it's just x times sine of 26 degrees. And x, we calculated to be 497.457 feet times sine of 26 degrees. So I've calculated an h value of 218.071 feet. Okay, and let's conform to two significant figures as given in the problem. So we'll just round that to 220 feet. Okay, very good. All right, in this situation, we have a guy lost in a desert calling 911. And there are two different cell towers spaced 22 miles apart that receive his signal. So we don't know his exact location, but each cell tower can pinpoint the direction the signal is coming from, and they both report the specific direction relative to where they are. And so where those two directions kind of intersect will be the location of the man. This is exactly what triangulation is. So, okay, the question is, how far is the guy from tower B? Well, let's draw a diagram of this situation. So the cell towers A and B exist laterally from each other. That's convenient. That means on the same east-west line. So let's call that tower A, and let's call this tower B. And tower A says the signal is coming from a direction 48 degrees north of east. Okay, well, here are the cardinal directions. That's north, and east is to the right. There's west and south. So 48 degrees north of east would be about this way, right? So it means that the 48 degrees is read that way from angle A here. So the guy is somewhere along this path, right? Now, cell tower B is saying we read him at 71 degrees north of east. Okay, so that would be an angle about like this, 71 degrees, which means the guy's right here. Okay, so the question is, how far is he from cell tower B? Well, we have an AB triangle, so we might as well just call the guy at location C here and use our standard convention, calling that a lowercase a, and calling this a lowercase b, and calling this a lowercase c, which actually is given as 22 miles. Okay. So, great. Okay, well, in order to use the law of sines, we need to have an opposite side and opposite angle pair known. So currently we only know one angle in this triangle, but I think we can see that we really know all of them because this angle right here is the supplement to 71, so that would be 109 degrees. And then we can find this third angle here, which would simply be 180 minus 48 minus 109. So that's a 23-degree angle. And now we have an angle and opposite side pair, so we can use the law of sines. Okay, and obviously we'll use it to find little a, because that's what's being asked. How far is the man from tower B? So we can see that little a over sine of big A is going to be little c divided by sine of big C. So little a is c times sine of big A over sine of big C. And we have those pieces here because little c is 22 miles times big A, which is 48 degrees, all divided by sine of big C, which is 23 degrees. So I get a value of 41.8425 miles, which we should round to 42 for the precision in the problem, two significant figures. So the man is 42 miles from tower B. Okay, well that makes sense because that's the answer to everything, isn't it?